Satyabama Institute of Science and Technology.
Hi everyone, I'm Dr. Mercy Paul Selvan, Professor, CAC Department from Satyabama Institute of Science and Technology. In this session, we are going to see an important topic called linear regression. Linear regression is a supervised learning algorithm which is used to model the relationship between two variables, that is x parameter and the y parameter. And it aims to find the best fit line which helps us to find the relationship. And it is a statistical method which is used to predict the outcome of unseen data in the future. Key concepts of linear regression are: what is dependent variable, what is independent variable. I told you we are going to figure out the relationship between two variables. One is x parameter, the other one is y parameter. Now that particular x parameter we call it as independent variable and y parameter we call it as dependent variable. Y is depending on x. So we always call y parameter as dependent variable or dependent parameter, whereas x never changes in the data set, so we call x as independent variable. And another key concept is linear relationship. We are going to find out the relationship between the dependent variable and the independent variable, assuming the relationship is always linear in nature. We can check out in the graph, represented as a graph where this x parameter is called as independent variable and y parameter we call it as dependent variable, and this particular blue line we call it as best fit line, which actually is a model figure out the relationship between x and y parameter. Why linear regression is so important in several fields, say for example machine learning, deep learning, artificial intelligence, data science, etc., etc. The interpretability of linear regression is very simple and it is one of the greatest strength of this particular algorithm. And it clearly gives us the clear coefficients that illustrate the relationship between two variables. And it is very simple and very transparent and very easy to implement as well. Okay, now the other key concept is best fit line. What is all about the best fit line? As we have seen in the graph, the blue color line is the best fit line. So our intention is to find out the best fit line for the given data set. Our main intuition here is the particular best fit line should cover all the data points given appropriately. Now this best fit line provides a straight line that represents the relationship, and the slope of this particular line indicates how much the dependent variable changes with respect to independent variable. Now in this figure, this is best fit line and this is x parameter, that is independent parameter. This is y parameter, we call it as dependent parameter. And when you look at here, all the red color points are known as data points. Each point represents one record. For example, one data point tells what is the corresponding x value and the corresponding y value. So all data points are the points available in the data set. After plotting those data points in the graph, we are going to put a best fit line. As I told you already, what is a best fit line? The best fit line must encompass all the data points in a closer proximity. So here, the dots over the line are called as predicted y value, and all the red points across y we call it as actual y value. Say like that, all the red data points, see this is a red data point yi, when you cross check, that is your actual y value. And when you check this particular black point over the line, best fit line, when you cross check the y value for this particular black point, this is ypi, which is known as predicted y value. And the difference between these two, we call it as error, that is yi minus ypi. We also can call ypi as y hat. And our intuition in the linear regression is always to minimize the error. That's when we can call the line as best fit line. So the error must be minimum. What is the error here? The difference between the red color y value and the black color y value, such that the difference between the line and the data points. So the intuitive part here is to minimize the distance between the line and the points. So your line should be able to cover all the data points appropriately, right? What are the assumptions we are going to take in the case of linear regression? The first assumption is it must be linear. The x data points and the y data points are linearly relatable. Okay, that is the first assumption we should have. The second assumption is independence. Okay, the observations in the data points are independent of each other. They are not depending on each other. All x and y values are completely independent. Homozygosity, that means the variance is constant over all the levels. This is another assumption we need to keep in mind. In the other assumption, it should be normally distributed. Your data set should be normally distributed so that it should follow the bell curve. Having these assumptions in mind, we have to go ahead. What are the types of linear regression? We have two types of linear regression. One is simple linear regression. The other one is multiple linear regression. Simple linear regression involves only one dependent variable and one independent variable. That's all. We have two parameters in the data set. Whereas your multiple linear regression has got more independent variable and one dependent variable. Let us look at the equation for simple linear regression. This involves one particular y value and one x value. As you all know, the line equation is nothing but y is equal to mx plus c or y is equal to beta 1 x plus beta naught. Here beta 1 is nothing but slope and b naught is an y-intercept. The formula for finding the slope is sigma x minus x mean multiplied by y minus y mean divided by sigma x minus x mean the whole square. First you have to multiply these two and you have to sum up for the numerator case. And the other type is multiple linear regression. As I told you, we have n number of independent variable. See here, you have x1, x2 up to xn. You can have any number of independent variables and of course you have to have one dependent variable. So similarly, you need to find beta 1, beta 2 accordingly up to how many x value we have and one y-intercept. Y-intercept is nothing but where exactly the line crosses the y-axis is y-intercept. And all slopes are nothing but the slopes. As I told you already, the change between x and y. We are going to solve the problem now. You will be given a problem like this. You will be provided a data set like this where you will have x values and y values. And the question normally could be, you have to find the regression line and for a particular x value, you have to find out the y value. Let us see how to solve it. As we mentioned already, this is a slope formula. You have to find the slope, right? Okay, for slope, what is the formula? X minus x bar multiplied by y minus y bar sigma divided by sigma x minus x bar the whole square. So this is your data set, x is given, y is given, you have to find out x minus x bar. So a priori you have to find out the mean value for x and the mean value for y. So you can subtract for each data point x, you can find the difference with respect to mean. So x minus x bar is 1 minus 3 is equal to minus 2. 2 minus 3 equal to minus 1. So accordingly you have to calculate this x minus x bar for all the x value with respect to its own mean. Similarly, you have to calculate for y minus y bar with respect to the average of y. Then you have to multiply these two values over here and you have to square up these values here in order to substitute all the values to find out the slope value. So we are having, as per calculation, we are calculating x is equal to 3, y is equal to 4 and x minus x bar, the whole sum up of that particular information is 10 and sigma, denominator part is 10 and the numerator part is 6. After substituting all the values, you will be able to come out a slope value beta 1 is equal to 0.6. Having that value, you can substitute in the equation. What is the equation for a line? Y is equal to beta 1 x plus beta naught. So beta 1 we had already calculated that slope value and you are going to find out the intercept by substituting the appropriate value. So y predicted is equal to beta 1 is nothing but 0.6 multiplied by, here x is nothing but the mean of x, multiplied by 3 plus beta naught. Okay, so accordingly if you substitute all the value, you will come up with beta naught as 2.2. So you are calculating slope and you have now calculated the y-intercept beta naught. So you can frame the equation y cap is equal to, that is y predicted is equal to 0.6 x plus 2.2. This exactly represents your model. Your model is nothing but the weights. Okay, what are the weights we had calculated? Slope and intercept. Once we have come out with a model, we have to apply all the data set value, that is x value, and you are able to find out the y predicted value. So what is the equation? Y cap is equal to 0.6x plus 2.2. So you should substitute each and every x over the equation, and you have to calculate the y cap for all the x value. So when you calculate, you have these values as y predicted. So as per this tabular column, you have x value, you have y actual value, you have y predicted value. This actual value is nothing but the data set value. Whatever available in the data set, the y value available in the data set, we call it as y actual. And y predicted, as per the model we had calculated, accordingly we will get the y predicted value. So what did I tell you? What is an error? The difference between the actual y and the predicted y, we call it as error. Now we are going to see what error you will have. I mean, what is the difference between y predicted and y actual. So that can be calculated by using MSE, mean squared error. So how do you calculate? You have to find out the difference between the actual value, y value, minus the y predicted value for all the data point. So what is your actual y? 2 is your actual y. What is your y predicted? 2.8 is your y predicted for the particular x value. So you have to put in the equation and you have to calculate, you will get 0.64. Accordingly, you have to calculate for every data point. Okay, these are error. So 0.64 is an error for the first x value. 0.36 is the error which based on our predicted model, this is an error. 1.00 is an error. So accordingly, you will have errors listed. So you have to find the average of all errors, that is nothing but mean squared error. Now another abbreviation is there. This is known as R squared. This will tell you how good is your model. Okay, you have predicted some model. Accordingly, okay, when you calculate the R squared, based on this calculation, you can figure out easily how good model, how good is your model, okay, what is your predicted model is good, how good it is, okay, we'll be able to figure out, right. So this is a formula, the numerator part, actual y minus y predicted the whole square sigma divided by yi, that is actual y minus y mean the whole squared sigma, right. And 1 minus, if you calculate, you will be able to get a measurement. Normally, higher the value, higher the model. In general, okay, it is not, you cannot evaluate, you cannot guarantee for it, but still, the higher the value, the higher the good, how good it is, okay. So that's how we'll be able to calculate the goodness of our linear regression. Hope it is very clear to you all. Thank you.